So let's take a look at our last section in Chapter 7. So the name of this section is Estimating the population, I'm going to abbreviate and say the population proportion with confidence intervals. So we're going to use confidence intervals to come up with an estimate for what we think is the population proportion, or the parameter for the population. We're going to use the central limit theorem to construct a confidence interval. Sorry, I didn't leave you a lot of room here. Confidence interval. So in this section, we'll turn our focus towards inferential methods of statistical analysis. Often it's easy to calculate statistics from a sample, because we always know what's happening with our sample. But it's difficult and sometimes impossible to calculate parameters from a population. And so when we take surveys, for example, we want to have an idea of what the population parameter would be based on our survey. And so our goal is to get the survey as accurate and precise as possible. So let's look at an example. According to PewResearch.org, a October 2016 article indicated that 685 out of 1,201 randomly surveyed adults favored the legalization of marijuana. So Part A says, what percent of adults surveyed support the requirement to legalize marijuana? So of the ones who were surveyed, what proportion supported that requirement? So what we're looking for is p hat, because this is part of our sample. Our survey is our sample. And so p hat for us would be 685 divided by the 1201. And as a percentage, that's about 57%, so 0.57 if we round it. Is the value in the previous question a sample statistic or a population parameter? Well, of course, that's measured on our sample, so that would be a statistic. Do you know the percent of all American adults that support the requirement to legalize marijuana? So they're basically asking us for the parameter P, the proportion of all adults who support this requirement. Well, I can't actually go out and ask everybody what their opinion is of this, so I don't know the true population, but I want to be able to come up with an estimate based on our sample. So it says, do you think the percent of adults surveyed who support this requirement is exactly equal to the percent of all American adults who support this requirement? In other words, is our sample proportion, that 57% that we got up here, is that going to be exactly equal to the population proportion P? And so the answer is no. I don't really have any way of saying for sure, but I don't think it necessarily would. So not necessarily. It might be close, and we want to try to get it as close as possible, but we can't say for sure that it's the same, that the sample proportion is the same as the population proportion. So from our previous sections, we know the following facts. Remember that p hat, our estimator, is unbiased estimate of the population parameter. And the reason it was unbiased, remember, is because we're pulling a random sample. Therefore, the population parameter P should be equal to p hat of 57%, or very close to it, our sample statistic. We can't say for sure that it is. It's not necessarily the same, but we think if it's an unbiased estimate because we've done a random sample, it should be pretty close to it. So our standard error formula, so we're going to use the formula standard error, and I'm using the little EST this time at the bottom. That's just a notational thing. You don't have to include it, but the idea is it's an estimated standard error. Because I don't know P, so instead of using P, I'm going to use p hat. Remember, we can always use p hat to estimate P as long as it's an unbiased estimator. So we're going to say p hat, square root of p hat times 1 minus p hat divided by n. And so for my example here, that's going to be 0.57 times 1 minus 0.57 divided by my sample size n, which was 1201. And I'm short on space here, so I'm going to come right over here. I'm getting about 0.0143 when I round it off. Okay? So because the sample size is large, the probability distribution of p hat is approximately normal. So I'm applying the central limit theorem. If you remember, the central limit theorem said as long as your sample size is large, and a couple of other conditions are met, that our sampling distribution is going to be distributed approximately normal and centered around the true population proportion or the estimated proportion of P. There's a 95% chance that P hat is within 2 standard errors of the population. Where am I getting this 95% from? That comes from the empirical rule. Remember that the empirical rule in a normal distribution or symmetric distribution says that 95% of the data is going to lie within 2 standard deviations or 2 standard errors of the mean or the expected value. So 2 times our standard error of 0.0143 gives us about 0.0286, and if we change that to a percentage, that gives me 2.86%. So we are 95% confident that the value of the true population proportion is within 2.86% percentage points of the 57 that we were expecting to get. So if we take 57 and we subtract that 2.86, we get 54.14 as a lower bound. And if we take 57 and we add the 2.86, we get 59.86 as the upper bound. And that's our confidence interval. So our confidence interval means that we think the true population proportion is somewhere between those boundary points. Let's summarize this. We are 95% confident that the population proportion, or the proportion of all American adults who support legalizing marijuana, is somewhere between those boundary points, 54.14% and 59.86%. So this is our confidence interval. So it gives us a range of plausible values for what we think the real population might be. So confidence intervals provide us with a range of, this is what I just said, a range of plausible values for a population parameter. It gives us a confidence level, which expresses our level of confidence that the interval contains the true population proportion, and it gives us an idea of how good our method is and how successful we think our method is. It tells us how often, so here, same thing, it tells how often the estimation is successful. If we were to keep repeating pulling samples from this distribution using this method, how often would those intervals contain the true population parameter? In this case, in our example, about 95% of the time. So it measures the success rate of the method, not of any one particular interval. Remember we said earlier in the chapter that statisticians measure the method we use to conduct that survey, and that's really what we're talking about here. So our confidence interval is based on something called the margin of error. And if you hear people talking in the news these days about polling data, you might hear a survey has a margin of error of plus or minus 2 percentage points. This is what they're talking about. It's an example of what they're talking about. So the margin of error, I'm going to give you a formula. It's kind of a funny looking formula, but I'll explain it in a second. The margin of error is computed using the formula Z star times the standard error. So Z star is a number that tells us how many standard errors to include in our margin of error. This comes directly from the empirical rule. From the empirical rule, Z star equals 1, for example, would correspond with an approximate confidence of 68%. So remember from the empirical rule, 1 standard deviation out from the mean contains 68% of the data. It's the same idea. Z star equals 2, what would that correspond with? An approximate confidence level of 95%. And Z star equals 3 would correspond with an approximate confidence level of 99.7%. And so this table here, I'm going to give you a table. This is going to talk about all of the Z star values that you might have to work with if you're computing one of these by hand. So a 68% confidence level corresponds with 1 standard error or Z star value of 1. An 80% confidence level, now when we talk about the empirical rule, we don't usually include 80%, but we could if we wanted to. It would be 1.28 standard errors out, or a Z star level of 1.28. 90%, again, we don't talk about that normally with the empirical rule, because we usually with the empirical rule we just count 1, 2, and 3 standard deviations out. But we could go in between. So 90% would correspond with 1.645 standard error, or 1.645 for the Z star value. 95%, and if we're being a little more precise, 95% would be 1.96 for the standard error, but we often just use 2 for that. or a z-star value of 2. And 99%, if we wanted to be 99% confident with our method, then we would use a standard error of 2.58 or a z-star value of 2.58. And a lot of times we're going to use StatCrunch to help us with these numbers, so you're not going to necessarily have to memorize these, but if you do need to calculate one by hand, you can always refer back to this table. And we'll do an example. I know it's probably a little bit fuzzy right now. Confidence intervals have the following form. So this is the thing. If you have to compute a confidence interval by hand, this is the formula you're going to follow. The confidence interval is always in the form p hat, so your sample proportion, plus or minus your margin of error. So you take your sample proportion, you add the margin of error, and you take your sample proportion, and you subtract the margin of error. So how do we get the margin of error? The margin of error is equal to z star times our standard error. Standard error formula is going to be used computing the square, using that square root that we used earlier. The standard error, so the confidence interval, so another way of expressing this is to say p hat plus or minus z star times the standard error. Don't get overwhelmed with the notation here. So let's kind of summarize what we did. We said p hat plus or minus the margin of error, but the margin of error is also found by computing z star from this table above times the standard error, or we could say p hat plus or minus z star times the standard error is our formula. And then the standard error, of course, what's that formula again with the square root? I'm using EST for estimate, but if you forget to write that, it's not serious. Since I don't know p, I'm using p hat. So p hat times 1 minus p hat divided by n is the formula we're going to use to estimate our standard error. So it says, note, since the confidence interval calculations are based on the central limit theorem for sample proportions, the conditions for the central limit theorem must still be satisfied when you go to create a confidence interval. So what were those conditions again? Remember, the sampling has to be random and independent. It has to be large enough to expect 10 successes and 10 failures, and we're going to use p hat to help us estimate what those should be. And the population has to be large enough so that it's at least 10 times the sample size. And we're still going to need to check those conditions most of the time. So let's do an example all the way through working one out by hand. Let's see what this is going to look like. So it says, during a recent semester, 63 of the 159 MAT223 students randomly surveyed said that they had had a negative situation occur to them based on a posting on social media. Let's estimate the percent of all Flagler College students who have had a negative situation occur based on a social media posting. So we've got a sample, and we want to use that to make an inference about the population proportion. So it says, what percent of the students surveyed had a negative situation occur based on a social media posting? So we're computing p hat here. And so for us, that would be 63 divided by 159. And that rounds to about 40%. What symbol would we use to estimate the proportion that we calculated in A? Of course, that was p hat, and that would be a statistic since it's a measurement based on the sample. Check the conditions of the central limit theorem to create a confidence interval. So is the sample random and independent? They said random in the question, so we can assume yes. Is it large enough for at least 10 successes and 10 failures? Well, the number of successes is going to be n times p hat. So for us, that's going to be 159 times 0.40, which is 63.6, which is certainly large enough. That's the expected number of successes. The expected number of failures is going to be n times 1 minus p hat. So that's going to be 159 times 1 minus 0.40. Of course, 60% of that is 95.4, which is certainly big enough. Finally, is the population at least 10 times the sample size? So our population, remember, is all Flagler College students. So if we estimate a population of Flagler College of around 2,500, so is 2,500 at least 10 times our sample size of 159? Yes, it is, because of course that's 1590. So our population is at least 10 times what we need for the sample. So let's calculate the standard error. So our standard error estimated is going to be the square root of p hat times 1 minus p hat. Make sure you see where I'm getting these numbers from. That's 0.4, remember, that was our p hat that we calculated in part A, divided by 159 for our sample size, and I'm getting about 0.039. So then it says construct a 95% confidence interval. So based on a 95% confidence level, what is the value of Z star? So 95 is probably the most common that you'll see, so you'll start to remember this after you do a few of them. But from the chart back here, remember Z star that went with a 95% confidence interval. We said the Z star value was 2, 1.96 if we're being a little more precise, but we can just estimate it to be 2. So our Z star value that we're going to go with is 2 because they asked for a 95% confidence interval. So then calculate the margin of error. So it's going to be Z star times the standard error estimated. So it's going to be 2 times the 0.039, and I'm getting approximately 0.078 for the margin of error. So to get the lower bound for the confidence interval, I'm going to take p hat and I'm going to subtract the margin of error. So that's going to be, let's see, my p hat was 0.4 minus 0.078. So I'm getting a lower bound of 0.322. And then to get the upper bound, I'm going to do p hat plus the margin of error, right? Because remember, it's p hat plus and minus the margin of error. I'm getting that from back here, this formula right here. And so I'm going to do 0.40 plus 0.078, and I'm getting a value of 0.478. And so then it says label the interval appropriately. So they want you to come up with sort of a graphical representation of what this interval would look like on a number line. So the middle is your p hat. So for me, that's 0.40. The lower bound would be p hat minus the margin of error, so 0.322. And then the upper bound would be p hat plus the margin of error, which would be 0.478. And so what does an interpretation of this look like? So we're going to say that we are 95% confident. Based on our method, we are 95% confident that the true proportion of all Flagler students who had a negative situation, so a negative situation because of a social media posting, is somewhere between, I'm going to make these percentages, 32.2% and 47.8%. And there you go. So we don't know what the true population proportion is, but we are fairly confident we have a range of plausible values. We think it's between 32.2% and 47.8%.